This is screencast 3.6 for AP Chemistry, another review of acids and bases. This is definitely the same stuff we've covered in the last screencast, but presented in a different point of view. So if you think you already got it, go ahead and skip it. But if you want to use this as another self-test, be my guest. Name 6 strong acids. Pause this if you need to. Did you say hydrochloric, hydrobromic, hydriodic, sulfuric, nitric, and perchloric? Hope you did. 6 strong bases. Wow, okay. Lots of group 1 hydroxides, and how about the group 2 hydroxides? So lithium, sodium, potassium, calcium, beryllium, magnesium, things like that. Arrhenius acids contain H3O+. It is semantic whether to call it H3O+ or H+. You'll see some textbooks do it other way. Perhaps the more correct way is to say H+, because anytime you have H+ in solution, it gloms onto water to make H3O+. So I wouldn't worry about it too much one way or the other. So for example, hydrochloric acid and water will make H3O+ and HCl and Cl-. It's the same thing as saying that hydrochloric acid dissociates in water to H+ and Cl-. The Arrhenius bases contain hydroxide in solution. So sodium hydroxide will dissociate into the sodium cation and the hydroxide anion. Ammonia is a case where it doesn't have OH- in and of itself, but it does form it as soon as it reacts with water. We call this a Bronsted base. See this right here? So that says Arrhenius base, but this is not an Arrhenius base. This is actually a Bronsted base. It generates hydroxide when it reacts with water. You may be fooled by substances such as methanol or ethanol that you see the OH present, and you might be wondering if it's in fact basic. But unless it's preceded by a metal or the ammonium cation, it's not going to dissociate at all. It's an organic substance that's covalently bonded there. They call that not a hydroxide, but an alcohol. Bronsted acid is defined as a proton donor. It has an H+ that it can give up. And a Bronsted base does not have to have OH-. It's defined as a proton acceptor. I've always preferred to think of a Bronsted base as a substance which generates hydroxide in the presence of water. Either one is fine. Okay, let's identify these as a Bronsted acid or a Bronsted base. We just pointed out that since there's no OH- present in ammonia, but it generates it in solution, that's the classic definition of a BB, a Bronsted base. All right, let's say if it's mono, di, or triproduct with an M, a D, or a T, and then let's also call it a weak or a strong acid. So this is memorization. Hydrochloric acid, monoprotic strong. Oh, that's the Bronsted acid. It's also an Arrhenius acid, isn't it? Since it dissociates to make exactly H+. So semantic there. It's both, really. This is a monoprotic strong acid. Nitric acid, what would you say for that? I'd say monoprotic strong. Acetic acid, classic example of a weak acid. This H right here is the acidic H+, the acidic proton, but it doesn't dissociate much. Notice the double arrows. This is a weak monoprotic acid, monoprotic weak. Diprotic, see the 2 H's? You can lose both of them. The first one easily, the second one not so much. That shows up in the next question. So this is diprotic strong. Only 1 H left, so it's monoprotic, and I don't think it gives it up that easily. We're going to call that monoprotic weak. Phosphoric acid, oh my God. TW, it's a weak acid, but it's triprotic. Interesting, triprotic strong. I don't think so. I think that's an error. See that? It's not listed as one of the strong acids. I think this should be TW. In fact, I'll change it. This looks like triprotic weak. I'm sorry, diprotic weak, monoprotic weak. This is some more definitions about acids and bases.